Welcome, everyone. I am absolutely thrilled to guide you through this explainer today. We're going to explore the dynamic, completely invisible engine that drives our entire universe, chemical reactions. But we aren't just going to look at what happens when things mix and bubble. No, we're zooming way in to understand the strict, microscopic rules of the game that govern exactly why and how fast these reactions actually occur. It's a fascinating journey from the everyday world we can see right down to the molecular level. Honestly, it kind of changes the way you look at everything around you.
Okay, let's dive into this. Here is our roadmap for today. Number 1, basics of chemical reactions. Number 2, 4 types of reactions. 3, the rules of collision. And 4, speeding up the reaction.
All right, Section 1, Basics of Chemical Reactions. To understand the game, we first have to identify the players on the board.
So, let's quickly nail down our core vocabulary. Chemical reactions basically involve atoms, ions, or molecules interacting to form entirely new substances. The materials you start with, the ones literally doing the reacting, are quite logically called the reactants, and the brand new substances that get created as a result, those are the products. Every single chemical game we talk about today revolves around transforming these reactants into products.
And these reactions, they're happening all around us, every single second. They're what make our physical universe so dynamic, colorful, and constantly changing. From the rust forming on an old bicycle in your backyard to those spectacular, fiery explosions in a chemistry lab, it's all just reactants becoming products.
Moving on to Section 2, 4 types of reactions. Let's run through the 4 main plays in our chemical game.
First up is synthesis. Just like the name implies, this is when 2 or more simple reactants combine to form a single, more complex product. You can think of it simply as A plus B becoming AB. A perfect everyday example of this is iron reacting with oxygen in the air to create iron oxide, which, of course, you and I know as rust. 2 pieces coming together to make one.
Now, what's really interesting about this next one is that decomposition is the exact opposite of the synthesis play we just looked at. Instead of coming together, one single reactant breaks down into 2 or more separate products. So A becomes A plus B. A great example of this is taking water, H2O, and breaking it apart into hydrogen and oxygen gases.
Our third play is single replacement. You can kind of think of this one like a game of tag. A single element steps in and replaces a second element that's already part of a compound. So if A reacts with the compound BX, A simply tags B out, leaving B on its own, and forming the new compound, AX. And finally, we have double replacement. This is a full-on swap. You have 2 compounds reacting, and they essentially trade parts to form 2 completely new compounds. The components just cleanly swap partners, instantly turning the reactants into an entirely different set of products. Section 3, the rules of collision. We've seen the big picture plays. Now let's get into the strict microscopic rules.
So, how do these molecules actually transform? Like, what is the actual physical mechanism that causes a reactant to suddenly snap apart and become a product? Let's zoom way down to the micro view to uncover the invisible mechanics of the universe.
Well, it all comes down to something called collision theory. This theory states a very simple yet absolutely non-negotiable rule. For a chemical reaction to occur, the molecules, atoms, or ions must collide first. Mere proximity? Not enough. They can't just be floating in the same beaker. Physical contact, a literal collision, is the mandatory first rule of the game.
But here's the catch. Just bumping into each other isn't an automatic victory. We have to divide these impacts into 2 very different categories. An effective collision is a successful one. It successfully leads to the formation of our products. An ineffective collision, on the other hand, is just a bounce. The particles hit, but absolutely no reaction occurs and no products are formed. Our goal, obviously, if we want a reaction, is to guarantee effective collisions.
Think about it like everyday life. If you have 2 people walking past each other on a busy street, but they don't actually physically bump into each other, nothing happens. They just keep on walking. The exact same is true for molecules. Rule number 1, they absolutely must physically collide. And this brilliantly illustrates the point. For any chemical reaction to even have a tiny chance of occurring, there must be a literal collision between the players. But remember, a collision is just the bare minimum requirement. They've bumped, sure, but is it an effective collision? For that, we need 2 more things.
Which brings us to rule number 2.
The particles must have sufficient energy, known as activation energy. Imagine a soccer goal. The ball, representing our particles, has to collide with the net. But if you barely tap the ball, it rolls a few feet and just stops. It collided with the ground, but it didn't have the kinetic energy to actually reach the goal. In chemistry, if the particles bump but don't hit each other hard enough, with enough activation energy, they just bounce right off. No reaction.
And rule number 3? Correct orientation. Nature is incredibly strict about this one. The particles have to hit each other not just hard enough, but at the exact right angle. If molecules collide side to side or wrong end to wrong end, it's just an ineffective collision. It's only when a specific atom strikes the exact right spot on the other molecule that the bond actually breaks and a new product is formed. It literally has to be a perfect strike.
Section 4, speeding up the reaction. Is there a way we can hack these rules?
We know these microscopic rules are incredibly strict. So can we hack them to make reactions happen faster? Oh, absolutely. We have 4 real-world cheat codes that we can manipulate to crank up the reaction rate, basically increasing the number of effective collisions. We can tweak the temperature, change the surface area or particle size, alter the concentration, or introduce something called a catalyst. Let's quickly break these down.
First up, temperature. By turning up the heat, we're literally giving the molecules way more kinetic energy. They move around faster and hit harder, which makes it much easier to satisfy that activation energy rule. Second, concentration. If you add more molecules to the exact same amount of space, you're crowding the playing field. With way more players rushing around in the same volume, the mathematical probability of them bumping into each other goes through the roof.
Third is surface area, which is directly tied to particle size. Think about dropping a solid, giant block of sugar into water. The water can only collide with that outside layer of the sugar. But if we crush that sugar into tiny granules first, we expose vastly more surface area. Smaller particles mean more exposed area, which creates tons more opportunities for those vital, effective collisions to happen all at once.
Finally, we have the ultimate shortcut, catalysts. A catalyst is a substance you add into a reaction that actually provides an alternative, easier pathway. It actively lowers the required activation energy barrier without actually being consumed in the reaction itself. It is literally like finding a hidden tunnel straight through a mountain instead of having to hike all the way up and over it.
Let's move this to the real world and see how this builds into massive global applications. We use these catalyst shortcuts everywhere to power major industries. In agriculture, we use iron as a catalyst to synthesize ammonia for fertilizers to feed the planet. We use zeolites for the cracking of petroleum in the oil industry. And right inside your own car's exhaust system, we use materials like copper oxide or platinum to rapidly oxidize harmful emissions. By mastering these tiny rules of collision, we literally build and maintain our modern world.
Which brings us to the end of our explainer and leaves us with a massive, exciting thought to chew on. We've figured out how to hack these microscopic, super strict rules using temperature, surface area, concentration, and catalysts to feed billions, power huge cities, and drive innovation. So, as we look to the future of science, I leave you with this. If we can do all that, what invisible collisions are waiting to be manipulated next? Keep looking closely at the world around you guys because absolutely everything is a reaction waiting to happen. Thanks for learning with me today.